Hello everyone, it's November 17th. Alright, let's do this. Frequency of the most frequent element. The frequency of an element is the number of times it occurs in an array. You are given an integer in nums and an integer k. In one operation, you can choose an index of nums and increment the element at that index by 1. Return the maximum possible frequency of an element after performing at most k operations. So we can perform at most 5 operations. Now we move everybody to 4, right? At most 5 operations. Only 2. We can move 4 to 8, or 5 or 8 to 13, or 1 to 4, but then you cannot move anybody else. Interesting. How did they come up with all these problems? So you can move at most k, right? K times, and you want to increase the frequency. The maximum possible frequency. Basically, how many numbers can you make it to be equal? So we have 1, 2, 4, right? Okay, find the difference is 1 and 2. So we can find an array which is difference, right? Basically, what we want to say is that's not true, right? So we want to find some values like +1. That's actually not true because we go to 4, right? So this is, nah, it doesn't feel right. So, but eventually we want to, or can we say if we, eventually if we sort, we sort the numbers, right? And the final answer is gonna be some one of them, okay? So now we just say, if we will match everybody to a certain value, then how many do we need? So if we distribute the k, how many do we need? How many can we make to be the same? So if we say if it's gonna be 1, then there's just 1. So nobody is smaller than 1. Actually, no, we can, because there could be duplicates. So this would be unique. So everybody has also a count. So if it's a 1, then we just a count of 1, right? If it's 2, right? If it's 2, then we see, okay, we have 1 value is, so we know the difference. Well, maybe we still need a difference, right? So the difference is 1, okay? And we can count how many 1s there are. Then we know how many increments we need, right? How many increments? How many operations do we need to make every one of them equal to this, right? If we have anything left, then we try to see if there's anybody in front of, to the left of 1, and see how many more can we break. So by doing that, for each one, we just go left, left, left until we run out of k. So now we can know how many in total for 2, right? Then we need to go to 4. So that's O(n) squared, right? It's not gonna work. It will work, but it's gonna be too slow. So can we speed it up? So basically we have, A0, A1, A2, all the way to AN. And if we have an AM in between, we say if we want to match everybody to this, okay? Then we want to know is the difference between this, the difference between this, the difference between this, right? We want to know these differences. And if we have the differences, it's just the sum of the difference. So, okay, there's a prefix sum. I can see a prefix sum like this. We know this, we can know this, we can know all the differences. And we will be able to know the total amount of operations that needed to equal to this, right? The total number of operations. Yeah. And then we can, for each one we can mod 5, mod the k, then we know how many can we do. But that's just to compute one, right? I can compute how many it will need to match to, I can compute how many need to match the an minus 1, right? I know how many it will match the an minus 1. We can just say, okay, well, an minus 2, an minus 3. Let's say we should just do all of this and part of this, right? Now we go to am. We know how many we need to match to am. How do we do that? Well, we can do am match to an, right? That's a match we can do. But how about these? Can we use what we have learned? Well, they need to match to this, right? So I know how many operations that I can support, right? For them to match to this. And if I want to match to that, so some of the operation needed to match that, then we have some operations left. Then what? So all of those need to add this additional thing, right? Need to add this additional thing. Or you can say what we want is just a count, the number, right? If we match the number, the count, we have the count, or just like dp, right? dp n minus 1. This is the count, the number of dp n minus 1, the number of the maximum possible frequency of element that can match to this, right? We have this, which is including this plus whatever previous. Okay. Then what? Then for the next one, well, if it's equal, we can just go. So this is the first one that's not equal. Okay, so this is the first one that's not equal. But here we have the maximum, right? We get the maximum. Basically, instead of maximum, so just it's a range, right? The range, all of this inside, the difference between everything added together, the smaller equal to k. Okay, that's what we have. Now we want the next one. Okay, we want to match to this. Then all of them, if they want to match to this, so everybody need to add additional, right? The difference between these two is the additional, because this first matches this, then have to add the additional. And this, I just say it has not only the dp count, but also how much did we use, right? We can say k prime, we use k prime out of k, right? Then so k prime out of k, we can do like another array, right? We can do another array. So dp is the count, we can do our OP, operation. So operation n minus 1, right? The operation needed to reach dp. Now for the next one, well, we need the operation. If we want to maintain dp, then we need dp this total number, right, times the difference between the two, right, times the difference between the two. That's the additional that we need, right? It's the additional we need. And so the addition, yeah, so it would be dpn minus 1 times the delta, right, times the delta is the additional. Is that delta? I don't think that's delta. Isn't delta... No, that's sigma. Dude, what is delta? Yeah, I think this is delta. Maybe. I'm not 100%. Hold on. Which one is delta? Greek letter delta. Oh yeah, that was right. That is delta. Right? So this times delta is the additional we need for everybody to match this. And it's not possible to get even more because this is already, dp n minus 1 is already the maximum that can match the n minus 1, right? And now you need to match the new one. So everybody need to add more. So you cannot extend more. So this is the maximum. So this is the additional we need to take, right? Additional we need to take. But we already taken this much, right? We already taken this much. And that means the total, right, it was going to be OPM minus 1 plus this, right? That's the total. But we cannot do that much, which means what we can do is this is the total amount, okay? This is the total amount. Then if we have 2 pointers, right? If we have a low pointer here, so every time low one go forward once, this additional can minus some minus until we cannot. So you're telling me that it's a 2-pointer? Maybe. It does look like a 2-pointer. So if we do 1, 2, 4, 2-pointer, so starting from here, right? So this is like an I like this to be J. And we will start, hold on, 2 pointers. So I, J, both are here at the beginning. Nah, we don't have to both at the beginning because we know the first definitely will work. So I and J, right? And then the difference. So this is the maximum on the left. And then the difference is smaller than K. So we're good, right? So at this position, we can record the result is equal to 2, right? Then J move forward. I doesn't change. J move forward, right? And then we count the current, we can say KK, right? Current is 1. And then we move forward, we need to add the previous, we have 2 previous. And if we want to match to this, each one need to add 2, so plus, right? So we say KK need to plus equal to the delta times the previous count. So it's equal to 2 times 2. So KK now equal to 5, which is still good. So now res is equal to 3. And then we're done. If it's smaller, then I need to move forward. Each time I move forward, we go, I think this will work. I think this will seriously work. One more. Okay. IJ. Okay, res. The difference now is, I mean, we can't, can we just like kick it off? You know, kick it off. Yeah, so the difference is j minus I plus 1, right? And then the count, previous count is 0, delta is 0. So yeah, if we start with delta is 0, count is 0, I equal to j equal to 0, everybody is 0. So now we start, okay? So when we start, what's kk? Kk is also 0 because of the previous, right? So kk is also 0. All right. So now the first thing we do is kk plus equal to delta times c. So kk equal to 0, smaller equal to k, right? So res will equal to maximum res j minus I plus 1. Perfect. And then after we do that, j move forward, I doesn't change. Okay? So now j is here. Okay? And then we compute delta first. So delta now is 3. Count or update. Count is 1. Right? And then kk is still 0. Alright. Now, in this case, kk will equal to c times, so it will be 3. Kk will be 3. Smaller equal to 5 is good, right? So now we'll update res is j minus I plus 1 will be 2. And c is also update to 2. Now, we'll move on. We'll move on to the next one, right? So it'll be 2. Okay, so j move on to here. So j is here, delta is 4. Alright, now c at this position, c is 1. But at this position, c become 2. And then kk become 3, right? Okay, so in this, we do kk equal to, so that's large, right? Too big. It's too big. So it's too big, so I need to move forward. So I say move 1, so I come here. So kk is, so total is 8, 11. So 11 minus 7. 11 minus 7 is 4, right? Kk equal to 4. So that was good. So kk now become 4. That was good. So it's still going to be 2, right? And next one, delta is 5. J comes here, right? And then we do, that's 14. That's too big. So I move here. 14 minus 9 is 5, which is good. So that's, yeah, I think this is the solution. All right, let's code it up. See, this I think is a medium, decent medium question. All right, so let's see how we're gonna do this. So first of all, we're gonna sort, okay? And then we have I equal to 0, j equal to 0, okay? Count is 0, kk is equal to 0, delta is 0, int res is equal to 0. Okay, everybody is 0. All right. Actually, we don't need to initiate j here. So we just say for int j equal to 0, j is smaller than nums, not less, j plus plus, okay? Here's what we do. First things first, kk plus equal to c times delta. Okay, perfect. And then we'll say if a while kk is larger than k, okay, then k larger than k and I is smaller than j, I will plus equal to 1, I plus plus, okay, I plus plus, and then kk minus equal to nums j minus nums I plus plus. until kk is smaller. Jump out. Okay, so now I want to get out. Kk is always smaller or equal to k. Okay, then we'll say c will equal to j minus I plus 1, and rest will be math.maximum rest and c. Right, and then we go back up. I just realized delta need to be computed. Okay, so delta, then why do you even need delta in the first place? Right, you're gonna compute it anyway. So that's just gonna be, oh, yep, I know why. Because delta, oh my goodness. What is delta? Delta is the current minus the previous, right? The current minus the previous. So in this case, I don't want to do another check. So we can do, how can we make this one? I'm thinking. I don't want to make another if call if I can help it. If I can help it. I don't think it's possible. Right? But J always move forward, so all right. What if we start J as 1? You know, I is 0, count is always 1. KK is 0. KK is the amount. So yeah, we need to do some documentation. Index of the left end. The number, the max frequency, right? The max frequency achievable if all, if nums, if nums j, if every possible numbers increase to nums j. Kk is the amount of operations needed to achieve C. Res is res, right? So the start j is equal to 0. Now we're going to do j equal to 1, right? So this is the delta. It's going to be nums j minus nums j minus 1, right? That's the delta. So this is the additional you need. And then we try this, right? If it's too big, then we do this, okay? And then we jump out, and C equal to this. Rest will be this. Go back up. J increment, so we can keep doing this. And eventually, we will return rest. So, okay, let's throw all these in. Give it a shot. Looks good. Submit it, and we will pass. Okay, edge cases. I didn't test the edge case. I'll put 0. Oh. Yeah, because we already have 1, so it's supposed to be 1. My bad. So it's just, you know, a slight oversight. Forgot to update this one. Good question. I think this is the essence, the epitome of a medium problem. And this is the perfect example of a medium problem. Solved with 2 pointers. Okay, so we sort nums first, and it is easy to see that if nums j, right, is the value with the max possible frequency, all the numbers that add up to nums j must lie on to the left, lie immediately to the left of nums j. Thus, we can use nums I, right, to mark the beginning of such subarray, of the subarray, right, of the subarray, that subarray with the max possible length. As we move j forward, each forward move would incur, right? And then if we use kk to mark, to record the total number of operations needed, right, to achieve the max possible frequency. As we move j forward, each forward move would incur an additional incur in total kk plus j minus I plus 1. Oh, we don't even need to use C though. But I think it's easier, right? It's this multiplied by nums j minus nums j minus 1. Right? If this new operation cost is smaller or equal to k, we don't have to shrink the subarray. Otherwise, we move I forward and reduce the new operation cost until the cost drops below k. Then we have the max possible frequency ending at nums j plus 1. It's actually j plus 1 because we move j forward, right? This is O1 log n because of the sorting, but the rest is just O(n). Oh, it's not bad. All right, check the solution. Sliding window. It's not 2 pointers. That's sliding window. Yeah, you can do that. Ah, you check every single time. Yeah, yeah, it makes sense. It makes sense. Right, every time you move it, then you check. And move it, you check. Yeah, it's advanced sliding window. How it is an advanced sliding window? We no longer care about any windows with less than len. Oh. We will not shrink the window. We will just try to grow it as large as we can. We'll keep the same condition. Ah. Instead of using a while, we just use an if statement. This means the left never increases by more than 1 per iteration, because the right also increases by 1. If we cannot find a valid window, we'll simply be sliding a window with static size across the array. If we add an element to... Ooh, this is interesting. So I think what it's trying to say is, hold on. All right. So you A0, A1, A2, all the way to AN, right? So you start from here, and then you move here. So you calculate how much you need. If it's good, then you don't move this, right? And you move here. And wait, how do you calculate this? Target, current. Oh, I never even realized it might need to be long. Plus equal to target. Oh, that's how they do it. I am computing the total cost. This is the compute. This is the prefix sum, right? Not prefix sum. It's like everybody to reach this. This is the prefix sum. This is the prefix sum. No, not really a prefix sum, but the sum of the window. This is the sum of the window. Like this is my KK. That's my KK, sum of the window. Okay, so yeah. So we reach here, and I have the current window, and I say how much, right? If it's good, then we keep moving. If it's too big, then I'll move it forward, right? I don't really care. I just move forward, and I check. Oh, that was good. Binary search. Now I'm not gonna go through binary search. Yeah, I have no interest in binary search. I'm interested in this extended. This is the extended sliding window from the official solution. What the hell? The key is that we do not have to shrink the window because we don't care if we don't care for a smaller window size. All we need to do is to expand it whenever possible, right? Whenever possible. Okay, so this is the left. We don't need this. We just need pre-sum. Okay, that's the prefix sum. No, not the pre-sum. This is the window sum, right? Result, we can start with 0, that's fine. And then j, we can start from 0, okay? And each time, window sum, right? We will plus equal to nums I, nums j, right? That's the window sum. And just j move forward. So that's the window sum. And then we say if we don't even need res. Say if nums j, right, times j minus I plus 1 is the total number. If everybody goes to j, right, as a total number, minus window sum, if it's larger than k, right, larger than k, then window sum minus equal to nums I minus I plus plus, right? So I can say this is current window too big, right? Current window too big. No, current window contains too many operations. Simply move the window forward. And we return j minus I plus 1. Give a shot. Of course, we also want this. Too much. Really? 4. Oh, j always go to the outside, so yeah. It is not j minus I plus 1 because j ends up out of range. Yeah, that's the one. That is the one. The best. I think my implementation is easier than this one, right? nums.length. Yeah, this is useless. Why even do that? Yep. Let's don't do this. J equal to 0, and this will be nums.length All right, that's it. Good. All right, let's see. How's this one going? You're given a zero-indexed integer array nums of size n representing the cost of collecting different chocolates. The cost of collecting the chocolate at the index I is nums I. Each chocolate is of a different type, and initially, the chocolate at the index I is of the ith type. In one operation, you can do the following with an incurred cost of x. Simultaneously change the chocolate ith type to I plus 1 mod n, such as to its neighbor to the right or wrap around. We can change the chocolate, so we change them, just swap them, right? Return the minimum cost to collect chocolate of all types. Huh? Given that you can perform as many. Wait, hold a second. Each chocolate. So the array is the cost of collecting different chocolate. The cost of collecting chocolate at index I. Okay. Each chocolate is of a different type. Each chocolate is of a different type. And initially the chocolate at index I. So how many chocolate do we have initially? In one operation, you can do the following with an incurred cost. Simultaneously change the chocolate of ith type to I plus 1 type for all chocolates. So wait, everybody move forward. So we're moving the numbers forward. I don't understand. I mean, to see the example. So initially the chocolate type are 0, 1, 2. Oh, we will buy the first type of chocolate until the minimum cost to collect chocolates of all types. So we'll buy the first type of chocolate at cost 1. Now we will perform the operation at cost 5, and the types of chocolate will become 1, 2, 0. So everybody shift to the what? Everybody shift to the left. Change the ith type, so 0's type, to, oh my goodness, yeah, it is shift to the left. I thought it's shift to the right. Yes, it's shift to the left. Then we will buy the second type at cost 1. Oh my god. Oh my god. So it's the position. Oh. It's the position. So this is the cost, is the position, right? So we have 21, 15. And the chocolate type initially is 0, 1, 2. So we want to buy, so basically what we want to do is to shift these around, right? Shift these around, and whichever position it end up, it will cost that. And we want to know what's the lowest cost. So yeah, we do this, we have 1, and we shift, we do it, we have 1, but we have a 5. So we have a 5 is the cost, all right? And then we can shift again. Then we buy. So in total is 13. 3 shifts till we buy this. And this is a 1, 2, 3. Okay, so again we start with 0, 1, 2. And we have 1, 2, 3. So we will buy this, shift once, buy it, shift once, and then buy it. And it tell me the answer is wrong. Because by doing this, you will take 1, 2, 3 plus 8. That's 11. But if you just pick them up, okay. So nums.length is, so have 1000 positions. Okay, so we have 1000 positions. And we just keep shifting to the left, right? We keep shifting to the left. So at each position, right? At each position, damn. How do we, how, minimum cost to pick every single one. Oh. All right, so you start with definitely, you try to find a minimum, right? You find a minimum, so you pick it. And okay, so here's the deal. You can always shift. So every single chocolate can be bought with the lowest price. Okay? Because you can always shift, just shift by one, it can be bought. So that's the cost to buy a chocolate. So if a chocolate can be bought at the moment, right, with a lower price than a shift, right, than a shift, then it is always cheaper to buy it without shifting, right? If I can buy the chocolate right now at a certain price, and if I need to shift it to go to another position to buy it, then we will have the cost, right? How much it will cost in total. So we can have, for each chocolate, right, for each position, right, each position, we can have the minimum cost it's going to need to purchase this, right? So we have the nums. So let's say for chocolate type 0, right? We can buy it here, it costs 20. We can buy it here, but that will require one shift, two shifts. Right? Require two shifts, so it's 2 times 5 plus 1. We can buy at 15, that costs one shift. So out of this, we can find, okay, the smallest is 11. Here, buy it as 1. Right? We can buy it at, yeah, I mean, it's systematic, so we have to compute everything. So we can buy it this, and we'll buy it here, we need one shift. So that's 5 plus 20. Buy here, we need 2 shifts. So 2 times 5 plus 20, right? And then, for sure, we can also do number 2. Buy it is 15. Shift 1, buy it. Shift 2, buy it. So that's 6, right? That's 1. That's 15. Right? So at the end, what we have is, why does it, because some of the shifts you're double counting the shift. Ooh, double counting the shift. Damn. All right, so the minimum cost. Yeah, you already count. So you will come out the number of shifts, right? So we have 2 shifts, 0 shift, and a 1 shift, right? And the final, yeah, we need two things. We need the number of shifts, and also the finally end up the cost. So we have this, so we 2 plus 1 times 5 plus 1 plus 1 plus 1. No, not 2 plus 1, just the maximum shifts, because these are free. So it's 2 times 5 plus 1, so it's 13, right? Okay, let me do one more example. 1, 2, 3. Okay, so nums is 1, 2, 3. We have 0, 1, 2. Okay, so for 0, we do, basically 0 shift. So should everybody be in array? Just the number of shifts. Yeah. So 0 shift is 1. 1 shift is going here is 3. 2 shift is 2. But how do you compute the cost? Right? How do you compute the cost? The cost. So if we do 0 shift, right? If we do 0 shift, I have the total cost. If I do 1 shift, I have the total cost. Nope. Nope. All right, I'm thinking again. Yeah, for 0, the cheapest is just to do this. For 1, the cheapest is also to do this. For 2, is also to do this. Yeah, it is. Like if you shift and then buy, then you will have a cost associated with it, right? And for each, can we say for each, we want to minimize the cost to buy each? Does it make sense? Because we're double counting the number, we're double counting the cost of shifting. That's something that I'm not comfortable with. Yeah, because if you don't, you don't shift, right? It's a 0. You have your cost, right? If we want to get this chocolate, we don't move, right? If we want to get a certain different cost, then we have to move that much, which means the cost of this is that much, right? But the cost of the others are not. Or, because at the end, you know the total number of shifts you need to do, right? The total number of shifts. So I just say, if I do 0 shift, I have the cost. And I say I do 1 shift, right? I do 1 shift. So if I do 1 shift, then we can compute. So if I do 1 shift, I have the cost, right? And I can compute for each chocolate, right? What is the cost of buying the chocolate right now, right? So the current smallest cost of the chocolate. The current smallest cost of the chocolate. So we start with 20 1 and 15, the current smallest cost of the chocolate for 0, 1, 2. Okay. And yes. Then we say, okay, let's shift 1. Okay, shift 1. So the current total cost is 36. Now we say we shift 1. So we shift 1, and everybody is +1 mod, right? Change the chocolate ith type to I minus I plus 1. So it's actually no, your is ith type. Change the 0 plus 1 type. So 0 become here, right? But we need to track. We need to track. How do you track what's the current cost, right? So because I want to track, right? I want to track the minimum cost. This is the minimum cost as 0 type, 1 type, 2 type, right? This is the current smallest cost. We start with this. Okay. Now we do 1 shift. So this will be +1? No. Each shift is this one move forward. So each one shall be -1 plus 3 mod 3. So this one come here, right? So we find its cost, and now we produce the current smallest, 15. Okay, 1 will be 0, current smallest still 1. 2, current smallest is 1, right? Current smallest is 1. So with 1 shift, right? With 1 shift, so this is 0 shifts. With 1 shift, our cost is 5 plus 15 plus 1 plus 1. Right, that's 22. Now with 2 shifts, so 0 minus 2 plus 3, right? So 0 will become 1. Right, 0 will become 1. So the smallest now becomes 1. Okay, smallest now becomes 1. And then 1 is still 1, 2 is still 1. So the total becomes 3. So it'll be 2 times 5 plus 3. That's 13. That will work. Okay, this will work. But I'm trying to see if we can find an easier way to make this. Yes, I think we can. 1 pass, we can do this. Okay. It'll take some efforts. It's a little bit convoluted, but overall, I think shouldn't be too bad. So here is the idea. We will make changes. No, we do not want to make changes. We will do this. Min cost, min c, go to new int nums dot length for int I equals to 0, I smaller than min c nums dot length I plus plus. We also need the cost, right? We need a cost, so we need a res. We need a current. Okay, so we do min c equal to nums I and current plus equal to nums I. All right, this I know we can probably do. Oh, my bad. What are you doing? Okay, right, so that's what we want. We have the current, we have everything. Now we're gonna start shifting, right? So for int shift s equal to 1, s smaller than, because the most you can shift dot length s plus plus, right? Shift 0 times, 1 time. So you shift 2 times, 1, 2, you go back to the same position. Shift 1, 1 shift, 2 shift, right? So that's the shift. So for each shift, I will compute a new cost. So it's the current, right? The current. So what we're gonna do is to find the mean C, okay? So we say, depending on how many shifts we have, for int I equal to 0, I smaller than nums dot length, I plus plus, right? The new index, okay, say when j, okay, we can put it here into j, okay, so j shall equal to I minus s plus nums dot length and mod num dot length. Alright, it's too many nums dot length. Let's just do int n equal to nums dot length. So all the nums dot length will become n. Okay, so will be this mod n. Okay, so this is the new, and then we say if mean ci is larger than nums j, then mean ci shall equal to nums j, but we need to make another change to the current shall be equal to okay, we can do current minus min ci plus nums j. All right, or we can do this plus equal to nums j minus min ci, and then we update min ci equal to nums j. Right, so we go through everybody and we make changes. After we finish, right, after we finish going through everybody, then we say rest shall equal to this is not what we want. Because this shall put here, that shall equal to current, so current cost, and we have int j, right? And then rest shall equal to mass dot minimum rest and number of this times x plus current, blah blah blah. We'll return rest. All right, let's see if it's correct. Let's try both. Yep, I think it's correct. I'm gonna put some. So this is the minimum cost, right, of collecting the ice chocolate after all the shifts, or all the changes, right? All the changes, all the shifts. This is the total cost of collecting all the chocolate at their respective positions they're shifted positions. So initially it will be the same, right? But as we go, this is update, right? This is update the min cost of collecting the ith chocolate after a shift. Okay. And find the min cost, right? Find the min cost of collecting all the chocolate after each shift. If a chocolate can be collected with a smaller cost previously, continue to use that previous cost. O(n squared. I mean, it's a hint for O(n squared because the total count is 1,000. Alright, try it one more time. Make sure everything works, and we will go. I absolutely hate this. It's my fault. It's absolutely my fault because I did not see. Okay? I did not see. So this has to be long. And this is fine. Current plus equal to, just cast it to long. Alright, I mean, it should be, let's change here. Okay, so long. This will be long. Oh, I think this is not necessary. This has to be long. Yeah. Cast to long. We will cast it for S. Okay, we'll do a long. Okay. Integer overflow. No, this won't happen in competition because if I do this in competition, we'll definitely Python it, so I don't have to deal with all this shenanigans. Okay. Not bad. Not bad at all. Alright, so why do people hate this problem? Description is wrong. Oh, yeah. Oh, yeah. Stack and a calculus. Too hard. AI contributes in a curve of trapezoid. A curve of trapezoid. So we can initialize rest as a second I don't think it means by deviation, right? It's derivative. I don't know. Yeah, integrated. I doubt this will be actually faster. Now I'm not gonna read it. I'll just call it. Come on, we do this for a hobby, right? Yeah, give yourself a little slack on this. Come on. All right, next one. Okay. All right, we'll end up today.